In October 1957, the world entered the space age. At that time, a multi-stage rocket took off from a launching site in Russia. As each rocket stage burned out, the next one fired. The last one launched the world's first artificial satellite called the Sputnik 1. The early satellites, both Russian and American, confirmed the work of scientists in many parts of the world. The first American satellite was called the Explorer 1. Its performance, and that of other satellites, was predicted by applying natural laws which scientists have learned through the years. What are some of these laws? Surely you've done this. As long as the ball goes fast enough, it's held out by its speed and pulls the string tight. The faster the ball whirls, the stronger the pull on the string. An Earth satellite is a free-moving body circling the Earth. It is held out by its speed and is held in by an imaginary string, the force of gravity. The closer to the Earth, the faster the satellite must go to overcome the increased pull of gravity. If you don't whirl the ball fast enough, eventually it drops. Let's look at this another way. Suppose there's a tremendously high mountain above the Earth's atmosphere where there's no friction with air. Suppose that on it there's a gun. A shot will soon be pulled to Earth by gravity, even though its speed is not reduced by air friction. If we use more powder, the shot will travel farther before it's pulled to Earth. But a charge that's just big enough will send the shot just fast enough so that the curve of its drop is exactly the same as the curve of the Earth. Since we've assumed that we're above air friction, speed isn't reduced. Therefore, the shot returns to the point where it was fired with the same speed it started with, and so continues to circle the Earth indefinitely as a satellite. If still more powder is added to the charge, the satellite goes so fast that it moves away from the Earth for a while, but then is pulled back and keeps repeating this path. This is an elliptical orbit instead of a circular orbit. If the gun isn't exactly horizontal, the same thing happens. Only a horizontal launch at a precise speed produces a circular orbit. Now, instead of a gun, let's use a rocket to launch our satellite. It's a very big rocket. Since there are no mountains high enough to reach above the Earth's atmosphere, the rocket itself must go that high in order to launch its satellite. Just how high is this? We've learned a great deal about the structure of the Earth's atmosphere. The first 6 to 10 miles we call the troposphere, which means turbulent. This is the dense churning layer close to Earth. It thins out to become the stratosphere, a stratified region that extends about 50 miles up. Then we reach the ionosphere, an even thinner region which extends some 150 miles up. Beyond this, single molecules and atoms thin out into outer space. Earth satellites can take various forms. The Explorer was encased in a rocket shell, which also included fuel for the final burst of speed. At its base, it was attached to other rockets, which would carry it to the necessary height. The Vanguard satellite was shaped like a ball spun out of metal. The first Vanguard satellite was not this big. The satellite shell is carefully fabricated to contain a complex assortment of devices for getting information and sending it back to Earth. This is part of the brain of the Vanguard satellite. Its many electronic circuits are powered by solar batteries. Solar batteries produce electricity from the action of sunlight. They operate the measuring devices and radio transmitters inside the satellite. The information which is broadcast back to Earth is recorded for further study. This is the brain of the Explorer satellite. Different types of measuring devices are sent up in various satellites depending on the information scientists are trying to get at the time. Here is the Explorer satellite, carefully covered, being hoisted to the top of the Jupiter-C rocket for installation. The first satellite launchings used multi-stage rockets, that is, a number of rockets fastened together, each one firing after the other has burned out, leaving the burned-out rocket behind. This rocket uses liquid fuel in its large first stage and solid fuel for the other stages. To enable the fuel to burn at high altitudes, the first stage uses liquid oxygen, which is extremely cold.
Personnel should evacuate the area at this time.
Takeoff of a rocket like this requires a careful checkout procedure taking many hours, called a countdown. It is conducted from a nearby blockhouse.
Count. 5, 10, 9, 8, ignition. Main stage. 4, 3, 2, 1, 0, plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
The early stages of the rocket's flight are tracked by ground instruments. Since we can't take a motion picture camera along into outer space, let's observe an imaginary three-stage launching by using animated models. The fuel in the large first stage burns out after about 2.5 minutes, sending the rocket very high. Then the first stage is left behind as the second stage takes over. In thinner atmosphere with less gravity, the second stage greatly increases the speed and height of the rocket. This stage often contains the guiding devices that put the rocket into the correct path for launching the satellite. Now the nose cone is released. It protected the satellite against the extreme heat of air friction. A motor makes the satellite spin to give it stability. With the rocket at the necessary height, the final stage fires briefly to produce the great speed needed for orbit. The satellite is then ejected, and if all has gone well, it goes into orbit, with the rocket casing trailing it. How high must a satellite go to stay in orbit? At a minimum of 150 miles up, air friction will bring it down in several weeks. At 500 miles or more, it might well stay up for centuries. Our first satellites have shown that the orbits must be higher than we thought at first because of unexpected air density at high altitudes. How fast must a satellite go? This depends on its distance from the Earth. The Moon, our only natural satellite, is about 250,000 miles away and travels at the comparatively slow speed of about 2,200 miles an hour. Closer to the Earth, where the gravity pull is greater, a satellite must go faster. At about 25,000 miles out, a speed of 7,500 miles an hour is needed. This satellite will circle the Earth once every day. At 1,100 miles out, a satellite must go about 16,000 miles an hour to stay in orbit. It will circle the Earth about every 2 hours. So there are many convenient orbits we can try to reach when sending up a satellite. Here is some of the information about outer space that the first satellites radioed back to Earth. Danger from meteor impact, very slight. Density of air at high altitudes, greater than expected. Temperatures extremely hot and cold on the outer surfaces of the satellite, but inside 50 to 80 degrees, a comfortable range for man. Danger from radiation in space, much greater than expected. This is the kind of information which was monitored from the first satellite's radio signals. Do satellites have practical uses? One suggestion is that several of them, equipped with television cameras, can report continuously on worldwide weather conditions. They can also be used to rebroadcast television to the whole world at once. But this is only the beginning. Already, rockets have taken animals into space to prepare for the day when man himself will make the trip. These films, taken in an actual rocket during a trip into space, prove that mice can survive launching and can stand conditions of weightlessness caused by zero gravity, as shown here by the floating ball. Men have been dropped out of high-flying bombers in rocket aircraft to probe extremely high altitudes and high speeds. In a new field of research called space medicine, men are being tested for the hardships of rocket acceleration and other difficulties they may encounter in space travel. We have designed spacesuits to keep up the pressure on the body to withstand extreme temperatures, to feed in oxygen and get rid of carbon dioxide. We are testing men under many conditions that they may eventually have to face in space travel. Already, many plans are being advanced for the coming age of man in space. One plan calls for prefabricated parts to be shot into orbit, to be assembled there into a giant space platform. It will include a great hollow wheel about 250 feet across, pressurized inside with living quarters and working space. This wheel will spin around 3 times a minute. The force of this motion will furnish a kind of substitute gravity for the people inside. There will be storage tanks for food, water, and other materials. Power may come from solar mirrors focused onto boilers. Indeed, it may be possible to focus solar mirrors onto parts of the Earth to influence weather conditions there. Here in outer space is a natural vacuum for scientific experiments, bigger and better than any man has been able to create on Earth. Here, beyond the interference of the Earth's atmosphere, is an ideal observatory that astronomers have long hoped for. In outer space, we can build a spaceship entirely different from any known on Earth, since this ship will not have to contend with the Earth's thick atmosphere and strong gravity. With this kind of ship, we may be able to explore far into our solar system. These are some of the plans being advanced for the coming space age. Fantastic? Who can say? Wouldn't our present uses of electricity have seemed fantastic when electricity was first discovered? We have entered the space age. Where we go from here, only man's imagination and ingenuity will tell.